Hi. Um, so this is going to be a video where I'll be going through the n-dimensional Gaussian integral with a source term in the exponential. And in doing that process, I'll also be explaining, the univariate version of this Gaussian integral and the n-dimensional version without any source term because both of those are relevant for this problem. Um, and yeah, I'm going to assume that you all have a background in linear algebra and in calc, like basics of calc 3, nothing too complicated, but multiple integrals and polar like change of variables, shifting to polar coordinates, stuff like that. Um, but if you don't have those backgrounds, then this might get a little confusing for you, but um, because I'm not going to spend a long time explaining some of that stuff. But yeah, I just thought this would be helpful because when I was learning how to do this integral, it was kind of like I like like this resource on it, the resources on it are kind of confusing, and so like this is just the way that I personally think through it the best. And yeah, with that said, I'll share my screen. Uh all right. Also, like I got this new like tablet pen writing thing. Um, and I'm not the best at writing with it. I'm still practicing, so my apologies if my handwriting is kind of messy. But this is the integral that we're going to be doing, and here we're going to assume that A is like a symmetric, positive, definite matrix. I'll bring that up again when we get to it. J is like a vector. X is a vector. And this is kind of basically what this integral is doing. This J term is is kind of shifting this multivariate Gaussian away from the origin, and it's also like kind of like stretching and squashing it. And so what this integral is going to evaluate is like what is the what is like the the integral, like the amount of what is under the area or the volume or of what's underneath this rescaled shifted Gaussian. And so that's this quantity that we're going to get, and we're going to it's going to be a number that we end up with, and yeah. So to start with though, like since the univariate Gaussian becomes really relevant, I'm just going to like go through that. We'll see if I uh, this writing thing is really tricky, but okay, I'll start with just doing this really simple case of negative infinity to infinity. This is one variable, um, and an exponent of negative 1/2 ax squared dx. So let me just really go over briefly like how to do this integral. Um, we can define this as we'll call it I. And something that's great about I is that we can also set this equal to negative infinity to infinity exponential. And again, exponential is just e raised to the power of whatever's in these brackets. Y squared. And see, this is like the exact same thing. So if we take I squared, we can multiply these two. And what we'll end up with, I'll just write it like this. dy. Um, and then we can move this inside. We can basically combine these things. And since we're combining them all and it's going to be like a product of exponentials, we can sum up these exponents and we'll basically end up with this. Now, this is a great candidate for switching into polar coordinates because in polar coordinates, oh, I really need to practice writing with this. In polar coordinates, we have x squared plus y squared equals r squared, and we have dx dy is equal to r d theta. So also when we switch to polar coordinates, we have to change these limits on the integrals because theta is going to go from 0 to 2 pi and r is going to go from 0 to infinity because there's no such thing as like a negative radius. So we have to keep that in mind and like make sure we have the right limits on our integral. Um, so I squared, now we're changing to polar coordinates, is equal to 0 to 2 pi and 0 to infinity of e raised to the negative 1/2 a, and then r squared. And now since dx dy becomes r dr d theta, there's an r here, which is going to make our life a lot easier evaluating this integral. Dr d theta. Okay, great. So now that we have this in polar coordinate form, we can do a simple u substitution where I'm going to set u equal to, and we're gonna first, what I'm doing is first we're going to be evaluating this inner integral. And so I'm going to set my u to be r squared over 2, which makes du equal to r dr. And look, we have r dr right here. So I squared equals the integral from 0 to 2 pi, integral from 0 to infinity of e to the negative au du d theta. And what this inner integral evaluates to is going to be I squared equals, I might stop writing this I squared in future steps, but like 0 to 2 pi, and then this is going to evaluate to negative e over a raised to the negative au, and u is and by the way, like the integral, sorry, the limits for u don't change, but when you're doing these kinds of substitutions, you should double check that these limits, whether or not these limits change. That's an important thing to keep in mind. Anyway, 0 to infinity, d theta, um, and oh, just need to charge my laptop real quick. Better. And so we are just going to subtract this uh, when u equals 0 from this when u equals infinity. And so what that is going to be 0 to 2 pi of so when u is equal to infinity, this is going to be, 1 over e like raised to the infinity because a negative exponent brings something into the denominator. So that's going to just be 0. And then this, when e is raised to 0, it's going to be it's just going to equal 1, which means that negative minus this is going to be minus 1 over a. Um but this, is going to turn into a positive, and this doesn't depend on theta at all, so we can bring it out of the integral. So we have 1 over a. Now this is just the integral from 0 to 2 pi of d theta. And so what that is just going to be is 1 over a times theta evaluated 0 to pi. And so obviously this is when theta is equal to 0, this whole thing is just going to be 0. So what we're left with is 2 pi over a. And this was I squared, which means that I is a square root of this. And I'll write the original integral too. Where it is negative. Okay, so we've just shown that in the univariate case, our Gaussian integral equals this quantity, square root of 2 pi over a. And now let's go back to our that full n-dimensional case. So just write it again. N exponent, where again, exponent just means like e raised to whatever's in this bracket. 1/2 x. I might stop writing the like vector. I mean, okay, I'm thinking about it, but like keep in mind that now we're working with vectors and matrices, but if I forget or if I accidentally stop writing this little like a vector symbol on top of x, just please keep in mind that it's now it's no longer we're no longer in one dimension. Okay. So, the first step is to complete the square of the exponential. And so this is just the extension of like the, algebraic expansion, but for matrices and vectors. And It basically says that when you have something in this form with like where x is a vector, j is a vector, and A is this matrix, and it's a square matrix. You can basically rewrite this you can do complete the square, which is like that trick from algebra, but with these matrices and vectors. And what you essentially get is now we're just looking at this thing in the exponential. Um, plus. And this is again just from the completing the square pro stuff from, but using matrices and vectors. And since this was in a power of e, now that we have this sum over here, we're adding a term to another term, we can turn it into a product of exponentials. And you'll see where I'm getting with this. Oh, I should note, just like I'm just gonna before we do that, I'm gonna just note that the multivariate, like the n-dimensional Gaussian integral with no source term would look like this. Um, yeah, I really need to practice writing this thing, sorry. So this is really important because you'll see pretty soon that this is going to become relevant. But anyway, so now we've divided this exponent into these two things. Now we're going to turn it into a product of exponentials because it was a sum in the exponential power. So I'm going to call this integral that we're evaluating ij. It's just the same thing we've been working with. And now I'm dividing you know, this is ij. And this is the same thing. Um, exponential. Okay, exponential. Okay. Um, oh, and I guess I've been using square brackets, but this is so this is oh my God. I'm bad at using this tool. Okay. Um, so now this and I'm just gonna write that it's dx1 dn. Um, So since we're depending on like these x's, we can see that this first part is just it doesn't depend on x at all. So we can move it out of the integral. So let's do that. It's just like a constant with respect to that. There's nothing that's going to change to it. Like there's no change to it. Like um oh, this is just supposed to be like a square bracket. And I'm just gonna start writing these x these like dx1 to dn as d to the n of x for like compact notation. And so like if you're, if you notice something cool about this is that we can we can do like a very clever change of variables here. So where we now set y, I'm going to call it y, equal to x minus a j. And when we do this, we can now, it's like something incredible happens where this integral now becomes mm, and this is just our n-dimensional Gaussian with without a source term. So now we can evaluate that. So now let's focus on evaluating that part of it. It's an n-dimensional Gaussian without a source term. So now we're going to, and this is just going, this is at the end, it's just going to be a product of that, the answer, the solution to this, and this other term that we found from completing the square. And yeah, it's a nice it's a nice solution. But okay, I'm gonna call this, I'll just call it regular I. And now I'm just going to be focusing on evaluating this part. So I equals um, exponent half y transpose ay d. Okay, so when evaluating this integral, there are a few properties of A that we're setting that make this really like nice. So properties of A. So A is symmetric and it's a positive definite matrix and real. Real. So because it's, positive definite, it means that it has positive eigenvalues. And since it's symmetric, it means it's diagonizable. I always struggle on that word. And this property that it's diagonizable is like it comes in so useful. And what does this mean again? So because A is diagonizable, it means that it can be represented as A equals B, D, 1, where D is a matrix that has all of like the eigenvalues of A on the diagonal. So D is like a diagonal matrix. It has um, the eigenvalues on the diagonal. Um, and also another property that comes from this is that since A is symmetric, it means that V and inverse are it's orthogonal, which means that basically you get this property. So that means that A can also be written as A equals V D transpose. Because and another property that we get from A being all these things and is that the determinant of V. Oh, what? Sorry, this is like I've never really used this before, but um I don't know what that was, but I made an arrow. Okay, anyway, the determinant of V is going to equal the determinant of V transpose, and that is going to be 1. It's unitary. Um, Okay, and so all of these properties are going to become really important like shortly when evaluating this. Oh, and I guess another thing to say is just that obviously like the determinant of A is going to be the product of all of its eigenvalues, but I'm going to write this notation as DI to represent the diagonal entries or like the non-zero entries of D. Um, because that is the way to use it later on. So yeah, the determinant of A is going to be the product of the eigenvalues, and the product of the eigenvalues are going to be the product of the diagonal entries of D. Okay, but anyway, let's get back to our integral. Um, we're going to do one more change of variables in a moment. Um, and since again, A is going to be equal to V D V transpose, um, I'm going to define a new variable P, um, and make P equal to V transpose Y. Okay. And now we can rewrite, if we just look at this part inside the exponent, Y transpose A Y is going to be the same thing as Y transpose. Now we're plugging and we're substituting for A, we're putting in this V D. Oh, what the heck? Sorry, I've like never used this like note-taking thing before. Um, what the heck is this? This is supposed to be a D. I, okay, D. There we go. V transpose Y. Um, and if we now, we can rewrite this whole thing as V transpose Y. Whole thing transpose D V transpose Y. And this is our P in both of these things. So now this basically equals P transpose DP. And if we actually say what this evaluates to, this is going to be equal to the sum. Like if you actually do your you actually like evaluate this, it's like and work through it. This is going to be the sum from I equals 1 to n of di pi squared, right? Um, okay. Now, remember we had that property that the determinant of V is equal to the determinant of V transpose, which equals 1. So dp, where we're going to look at P here, is going to be equal to V transpose dy. But this is just the same thing as 1 dy, so that's just dy. So which means we can just like literally plug this in. Like we can literally just use this as a substitute. So our new I, we can now write as this, where we're replacing what was in y transpose ay with this new thing because of our change of variables. N exponent of, I think I'm getting better at like writing as this video goes on, with this pen. Oh, I spoke too soon. It's like, what the heck is this? dp. And it's just dp because of what we just said. We just said that it's the same thing as dy. Okay, so what is this really? It's going to be equal to, we just evaluated that P transpose dP is this summation, right? So let's write that. Let's write that in. R to the n exponent. And this is going to be, I'm going to bring the 1/2 into the summation because it's the same thing as keeping it on the outside. It's just multiplying everything. Oh, yeah. Plus 1 to the n. We're so close to being done. Literally, we're so close to being done. 1/2 di pi squared. And you might see where this is going at this point, but it's going somewhere very satisfying. I guess I should have written, yeah. Um okay. And now, since we have this summation in the exponent, we can turn it into a product of individual exponents. And I'm going to also like to make this really clear, um, exponentials, write the integrals as, because this is really what we're doing, right? It's a bunch of these integrals. Um, Sorry, I remember this pen or like this like electronic pen is really being weird. Um, and it's going to be a product of each of these like individual 1/2 pi squared. Right. And so if you notice here, like each of these things inside the exponential, each pi, it's only going to depend on one of the pi's over here. So so since they're not interacting with each other, we can move this product on the outside and this becomes a product of univariate Gaussian integrals. So now we have I is going to be equal to the product of I equals 1 to the n of just a univariate Gaussian integral, negative infinity to infinity, exponential negative 1/2 d I pi squared dpi. And we did this at the beginning. We literally know what this univariate Gaussian integral is. This whole thing, and like, literally just did this at the very beginning, but it's going to be equal to 2 pi over di, right? You all remember. Because we just had a instead of this di. Um, so it's going to be a product of a bunch of these 2 pi, a square root of 2 pi over di. So let's write that equals the I equals um, product. Oh my God. I equals 1 to n. So I with the square. Ugh, I don't know. I'm literally just trying to write. I'm not trying to draw weird like symbols. Oh, that was like a horrible. Oh, and I deleted that, but okay, let me rewrite that. Sorry, I'm like really practicing using this tool. Um, 2 pi over di. And what this is the same thing as 2 pi to the n over the product I equals 1 to n with these di's. And if you remember before, the product of these di's, these are the diagonal entries of the eigenvalues. They're sorry, that the diagonal entries of D, which are the eigenvalues of A. The product of all of those eigenvalues is just going to be the determinant of A. So what we have is the square root, the answer to this I, this, this part of the full thing, 2 pi to the n, and this is supposed to be a square root, determinant of A, of our matrix A. Great, so now we literally have the full solution to IJ. If you remember before, IJ was equal to, I'll write what we had before, exponential of, actually, you know what? I'm gonna write like literally the full original integral because we're literally at the point where we have a solution. So I'll write the problem that we began with to start with. Okay, so we started. So our original problem, right, was evaluating this IJ equals integral from space of this n-dimensional Gaussian exponential negative 1/2 x transpose A x plus J transpose x d x, right? And so then we, after completing the square, we had shifted it into, or we had rewritten this as exponential of 1/2 J transpose A inverse J. And then we had our n-dimensional Gaussian without a source term. And after doing some change of variables in the first place, we had rewritten this as right. And then we evaluated this multivariate Gaussian integral we evaluated this and we got that it was this square root of 2 pi to the n over the determinant of A. So we have our final full solution, IJ is equal to, I'll write it, I'll write it as E. E raised to the 1/2 J transpose A to the negative, or A inverse J times our result from the n-dimensional Gaussian without the source, Gaussian integral without the source, n over the determinant of A. And this is our full solution to the multivariate, or to the n-dimensional Gaussian integral with a source term J, where again, that source term J is like shifting and rescaling the Gaussian. And just, for a sanity check, you can make sure that it's going to evaluate to a number. But yeah, that's it. Thank you so much. And that's all.